Sorry, there was an internet connection issue. So is this clear now? Like when we see that splitting and we have the two options where one is giving splitting, one is not giving splitting. So just looking at the spectra, we can get to know which one is what. So is there any doubt here?
Okay, ma'am, I understood.
Okay. So in the next case, when we were saying that turn bull true also, even if in case of turn bull blue, it is having this kind of structure where CN2. So the outer one is Rn2 and the inner one looks to be Rn3. But it is also giving us the same spectra as we were getting for the Prussian blue. So why is it happening? How come both the things are having different chemical formula, but still they are same? Why is it happen? Because here occurs an electron transfer from the Rn2 to Rn3, and therefore it makes it the similar kind of Rn3 high spin as the outer one and Rn2 low spin as the inner one. So this is the same case as Prussian blue. That's why in case of these two complexes which are having different chemical formulas, and one is ferro, one is ferricyanide. So in this particular case, when we look at the MOSFET spectroscopy, when their spectra looks to be exactly same, there we got to know that what is happening. There the Rn2 in case of Turnbull blue, it is leaving or giving one electron to the inner iron. Therefore, it is making the inner one as Rn2 and it itself becomes Rn3. Since it is outside, it will make a high spin, and inside one is bound with Cn, it will remain as low spin. This is the similar case of Prussian blue. So is this clear? This is very important concept, like why the two different complexes are having similar kind of MOSFET spectrum.
Okay, ma'am, I understood.
Okay. So next example that we are having is if we have this kind of complex where we don't know what kind of geometry it is going to take. We already know that carbonyl can bound as a terminal carbonyl or it can bound as a bridging carbonyl. Bridging could be between the two metal centers, or it can be among three metal centers when I'm taking this particular case, right? Where its electronic contribution remains the same. That is, it involves two electron contribution, it will give you two electron on. So first case that we have is iron, when it will be like in triangular shape. So first case, like all the carbonyls are bound as terminal one. So we have 12 carbonyls. So 4 will be given to all three of them. So that's our first case, right? The second case that we could have is iron. So here there is a possibility that we can have carbonyl as 50% bridging and other carbonyl as 50% terminal. See, for example, carbonyl, all the three irons would be having two terminal carbonyls and two bridging carbonyls would be joined with the centers. So here 6 carbonyls are bridging, 6 are terminal. So this is second possibility. Third possibility that we have is one is having 4 terminal carbonyls and the other ones are having 3 terminal carbonyls and 2 of them are bridging with them. So in this particular case, in first case, when all of them, they are having only the terminal carbonyls and all three irons are same. So what do you think? How many different kind of MOXPA spectra, like peaks you can see in your spectra?
In A structure, we get only one type of Moss Bayer signal
Right.
because all the iron is in the same environment.
So there is no bridging available, only terminal are there and all three are of similar type. So therefore they would be having only one type of signal. Now talk about the B. So here iron, three irons are having two terminals and two bridging. How many different types of iron are there?
Only one type of iron is present because all are in the same environment. We get only one type, only one Moss Bayer signal.
Right. So what about the C? Let's say, for example, I'm talking about this as
C structure, three iron is in three different environment.
just check it carefully.
No, two, because below the F, AA, that is the AA, that is the same environment.
So
Another one is the top FE is a different environment.
Right.
So the two signals.
So the A1 is one type and B1 is one type. A1 is having three terminal and two carbonyl as bridging, whereas B type is having all the four as terminal. So we would expect two types of signals in case of the MOSFET. And from the MOSFET spectra, we got to know about, and also you need to see whether these two are A are 2 in number and B is 1 in number. So we expect whatever the spectra comes, it is 2:1 ratio, right? So here we got to have the spectra. When we found for this complex, we found that there is one kind of splitting and there is another kind of splitting also, which is 2 times more the other one. So what do you think? Which one is A and which one is B? A1's for 2:1. So which spectra is for A iron and which spectra is for B iron? This I will make it with this blue color. This is blue shaded.
The blue shaded region of peak is 2. Red shaded region of the peak is 1.
So this one is the A type and this one is the B type, right? And therefore, now we got to know from the spectra, okay, iron 3 CO12 is existing as this spectra. And we also say that iron 3A is this particular splitting and B is that particular splitting based on the intensity. But how do we confirm also? In iron A, we saw that iron is in carbonyl connected to 3 carbonyls which are terminal and 2 carbonyls are bridging with the other one. Like this kind of shape it was having, right? The other iron is there. It is having all the CO terminal. So when we have this kind of system where all the terminal COs are there, and the other one is having more unsymmetry compared to the other one. So these ones are having like out of the A and B, this is A and this one is B. Which one you feel is having more asymmetry?
B is unsymmetric.
B is?
Unsymmetric.
Just check one more time. Why, on what basis we are saying it's unsymmetrical? In case of B, we have only the terminal carbonyls. So it's only one type of ligand is connected, right? Whereas in case of other metals, which are A, they are having both bridging as well as terminal. So now tell me which one is more asymmetric? The complex.
That is A iron is in the structure. That is asymmetric structure, ma'am.
Because it is having two different types of ligands, right? ligands are same, but the mode of binding is different. So when we have this kind of behavior, we can't directly say, okay, because all the coordination are almost more or less different. So we cannot compare on that ground. But we have to see what kind of different types of modes are present. In case of B iron, that is having only terminal carbonyl. So it is only symmetrical with respect to the terminal carbonyl. But in case of the A type, it is having both terminal as well as bridging. That's why it is called as to be more unsymmetrical compared to the B1. If I am having some red balls, and if my all balls are red, that means that is symmetrical. But if I am having a combination of red balls also, blue balls also, even though the ball size is same, but the colors are different. Similarly, here the binding mode is different, the ligand is same. So when this kind of scenario appears, we have to see what kind of binding mode is present. Whether all of them are terminal, then we call them as a symmetrical, more symmetrical. And if not the same bounding mode is present, that means they are more asymmetrical. So is this clear?
Okay, ma'am, I clear.
So when there is more unsymmetrical structure is there, that means it would be having more delta EQ. So the outer one becomes, it clears from here also, intensity also, but also from the delta EQ value, delta EQ is more for A compared to the B1. Okay.
Okay, ma'am.
Quickly, we will take up the last, it's only 10 minutes left, but we will quickly understand the effect of, this is the last topic of this lecture, effect of ligands on the delta value. So say for example, we have iron 2 complexes where the ligand are like this. If we have nitro, NO positive, carbonyl, NO2 negative, then we have NH3, then we have H2O. So the delta value goes like 0. If the source and sample both are same, so value, that means it's not moving, so it's 0. We are taking it as a relative standard value. With respect to this, carbonyl will give you 0.15. This is 0.26, 0.28, and 0.31. Right? We have already known that strong field ligands are going to give you low spin complex, and that would be having, when we have strong field ligands, that means they are pi acceptors. And when the pi acceptors are there, they will take up the electron density. So d electron density reduces. Therefore, there would be less negative. When it is less negative, when you can see, sorry, it would be more. When we have d electrons effect is less, that means shielding effect would be less. When shielding effect is less, this s electron penetration would be more, and therefore it would be more delta negative. So more delta negative, that means less delta positive. So if you will see, compared to these ones, NO positive is more pi acceptor compared to the carbonyl and compared to the nitro. That's why it is 0. It is 0.15, then 0.26, where if you go down, more pi donation or sigma donation is happening in case of water. That's why the delta value is more positive. So here it comes like this particular way. So what generally happens if we have metal orbitals, like this one, and ligand orbitals like this one. So here, when there is head-on overlapping, so this is your internuclear axis. Normally we know that Cartesian coordinates goes like X, C, and Y, and Z axis we consider as an internuclear axis where the nucleus are having the more electron density, like nucleus are surrounded, or they are along that Z axis. So if this is your internuclear axis along which your nucleus is there, and if you see more electron density is over there, when more electron density is there, that means it is a metal to ligand or ligand to metal. So here ligand to metal sigma donation is happening, and that is head-on overlapping. That means more electron density is there. And also we saw in group theory that when I'm giving it a C2 symmetry, like if I'm flipping it at a 180-degree rotation, it would be coming as a similar form. There won't be any change in the lining of this M and ligand, metal ligand orbitals. So therefore, on C2 rotation, if it is giving me no change, that is unchanged, therefore it calls as a sigma interaction. And this is called as a sigma donation ligands, right? So if on the other hand, we have side-on overlapping where metal orbitals are like this way and ligand orbitals are parallel to this one. So this is a pi donation from the ligand to metals. And if you will now, this is your internuclear axis. If you do the C2 rotation, there would be a flipping of the orbitals. So on C2 rotation, it changes. The symmetry changes. Therefore, it is a pi interaction. And here it is pi donation. It could be other way around, that metal is donating the ligand, the pi electrons to your ligand orbitals. That is also comes under pi interaction. So what are the groups that are involved in this one? If we have group 17, that means chlorine, fluorine, bromine, iodine, they are only involved in sigma donation and or the pi donation. So they are the weakest ligands, right? Now, if I'll talk about the group 16, there we have oxygen, sulfur, and selenium, which can be oxide form, sulfide form. There would be thiol form, or it could be water form also. So in these particular case, we have sigma donation and pi donation. This also comes under the weak field ligand category, but more compared to the group 17, right? Now we have group 15, where we are just having NH3, R2NH, that means primary, RNH2 primary, R2NH secondary, and R3N tertiary kind of ligands. That would be having only sigma donation. There is no pi is present. So they are also weak. Now coming to the group 15, but it is N double bond X. That means N double bond C, that cyanide group, N double bond C, N double bond O nitro group, N double bond C. These kind of things are over here. It would be having sigma donation, but more than that, it would be having pi accepting property. When pi accepting is there, that makes them a strong ligands. That is why in case of, if we talk about these things, these are strong field ligands compared to these ones. This will only be having sigma donation. This would also be having sigma donation, and these are having pi acceptor. That's why the value becomes more positive when we have weak field ligands or more donation is happening, because when more donation is there, more d electrons would be there. When more d electrons are there, they will shield your s electron density, and therefore less negative but more positive. Whereas if I talk about the pi acceptor, if you say this is positively charged, this is neutral, and this is negative. And here also it goes a similar way. When some positive species is there, that is creating more effect of your, the d electrons is more over there. That means pi accepting property becomes very high, and therefore you get to have a less delta value. That delta value is 0 in that particular nature. If I talk about the negative value, the NO positive would be more pi accepting, and that would be having more negative delta value, because the d electrons have been taken up. Because nitro that is having positive charge, that means it is deficient. But when it is deficient, it will take up the d electrons more towards itself. When d electrons it is taking or attracting more towards itself, it would be having less shielding effect. When less shielding effect is there, the s electron penetration would be more into the nucleus, and that will give you more negative delta value. That's why comparing here, if we talk about the positive term, that becomes a reverse. If it is having more negative, that would be less positive. So is this concept clear? In case of carbonyl, it is neutral compared to the positively charged and the carbonyl. The neutral one would be having less d electron acceptance compared to the positively charged, because the positive one is deficient. And if we have a nitro, NO2 negative, so if we have a nitro over there, that negative would be having already electron densities there. So it would be taking up the electrons, but not at that particular extent that we were looking at it earlier. So whenever we have a comparison of the pi acceptor ligands, you need to see the charge also, where it is having the NO positive, because in water case it's sigma donation also, pi donation also, so all the donation is possible. That's why it is more positive compared to the NH3, where only sigma donation is happening. And where we have a pi acceptors, where one is positively charged, one is neutral, other is negatively charged. The negatively charged will be already having electrons, so it will not prefer to take up the d electrons, and therefore the accepting power would be less, and more positive delta would be observed. Whereas in NO positive case, it is deficient. It will take up the d electrons from metal. When it is taking up, it will increase the negative delta value. So this way we can have the effect of the ligands. So is this concept clear?
Okay, ma'am.
Okay. Now let's see how many questions we can take up today. So we have choose a correct formula for A, that is Prussian blue, B is Turnbull's blue. So can you please answer which one is what? So in Prussian blue, we got to know that Prussian blue is having outer one as iron 3 and inner one as iron 2 low spin. This is iron high spin. So if I'll cross multiply, iron 2 inside is only possible when outer one is having this 4 in nature. 4 negative and 3 positive. So it will become iron 4, FeCN6, 3. So this formula is for the Prussian blue, and only the first option is, and this last option is having iron 4, FeCN6, 4, 2. Now look at the Turnbull's blue. We have seen that formula says iron 2 is outside and iron 3 is inside, where when the electron transfer happens. So when this is the case, it would be 3 and it would be 2. So the first option is correct. So you can work on this formula. With the practice, you will get to know about which one is what. And you can understand this Prussian blue is having ferrocyanide inside, and this is having ferricyanide, because the oxidation state is more in case of Turnbull's blue. So is this clear?
Okay, ma'am. Clear.
Okay. So we already know that what is the reason for the Prussian blue and Turnbull's blue to show the same OSPAR spectra. Even though their formula are different, iron 3 is outside in case of Prussian blue, whereas iron 3 is inside in case of Turnbull's blue. But why the OSPAR spectral looks to be similar? The options are electron transfer happens in Prussian blue. B option, electron transfer happens in Turnbull's blue. C, electron transfer happens both of them, or none of the above. So this is very straightforward answer. Can you please try it?
Electron transfer happens in both Prussian blue and Turnbull's blue.
No. Actually, see, we know that the MOSFET spectra says that outside is the high spin iron and inside is the low spin iron. So in case of Prussian blue, it's fine. But in case of the Turnbull's blue, it is opposite. So only in case of Turnbull's blue, the electron transfer happens when it goes from iron 2 to +3. So it becomes iron 3 outside and iron 2 inside. If you will say that in case of Prussian blue also it is happening, if you lose the electron from iron 3, it becomes iron 4. Whereas no spectra is there for iron 4 over there. And low spin would become iron 1. So have you seen anywhere that Prussian blue and Turnbull blue are having 4 and +1 oxidation state? So the only electron transfer happens, that is in case of the Turnbull group. That's the B option. Okay.
Okay, ma'am.
Now, tell me that choose the correct option for Prussian blue. In case of the Prussian blue, which oxidation states